Now today, I will start the quadratic surfaces, 12.6, quadratic surfaces. So far, we have seen the planes and lines. If you notice that planes and lines doesn't have the square something, yeah, they are not in quadratic form. They are in the linear form. But in space, of course, there are quadratic equations. Although we don't know all of them exactly what they are, okay? But we know, okay, bunch of those surfaces, and then we can represent them using some nice equations. The general definition of the quadratic surfaces, actually, guys, can be given by this formula. All right? This is the most general form of the quadratic equation in 3D space. But it is not easy to deal with this one. That is why, okay, the genius mathematicians, they did some rotation and then translations, guys. And we know that we can translate them into these using rotations and translations. We can reduce this one, okay, either this one or that one. Ax squared plus by squared plus zz squared plus j, which is equal to 0, or ax squared plus by squared plus iz, which is equal to 0. Well, I'm gonna show it to you soon, Alex, don't worry. After k, this is 0. That part is equal to 0. I need to scroll to the right a little bit. This is 0. Since that's the equation, that's a constant, and then that should be an equation, right hand side of the equation. So whatever you play, okay, in these days, they intensively used, okay, translation and then rotations in 3D spaces, guys. And then trust me, okay, they use a lot of analytical geometry and all of these similar type of the mathematical equation. 0, guys, 0, what do you expect? What could it be? 0, these are 0.
I meant the last letter in that first of the two equations.
What letter?
What is that after CZ squared?
What do you want it to be? Doesn't matter. D.
Okay, thank you. Sorry.
Sorry about that, guys. Sometimes my handwriting, the actually pen affects my handwriting. I don't claim my handwriting is nice, all right? I know nobody likes my handwriting, but I think I need to work a lot. Work more than multivariable calculus to fix my handwriting. Sorry about that. All right. So what type of shapes we are going to see today? As you remember, right? If you remember, we already saw the spheres, right? Spheres have this type of equation I showed you before. You see? Which is kind of right, it fits to the first equation actually. Which is just a translated version of that one. But first of all, today I'm gonna start by the circle, the cylinders, sorry, cylinders. The cylinders are not always the circular cylinders. Sometimes there are some different type of cylinders, guys. There's a definition in your book. I wanna give it to you. A cylinder is a surface. That consists of all lines that are parallel to a given line, and pass through a given plane, curve, All right. If you remember, right, I also showed you one type of the cylinder before, like this one as an example. I will show you some example. X squared plus y squared, which is equal 4, something like that. As you see, one of the variable is missing right here. It is a quadratic, and then z is missing. If the z is missing, that means actually z could be any number. Z is a random number here. If z is a random for any z, you need to draw a circle, right, on the space. That's what it means. For any z, you need to draw a circle. That could have another form. Look at that. I can miss one of the term and I can create this cylinder. Sorry. I didn't mean this one. Or I can create this cylinder. Right, guys? Something like that. All of them are cylinders. Let me not use my terrible drawing skills. Instead of, I'd like to show you one of the nice, this one, for example. You see? This is a cylinder. What equation is this? Z squared plus y squared, which is equal to 4. I can change z by x, x. This time, this is going to be a cylinder. All right. If you see the trace, we call the trace. Okay. Look at the trace of the cylinder, right, on the plane of z is equal to. So the trace, right, traces are just a picture of the surfaces on the specific plane. If you look at, right, the surfaces, traces of this plane, it's going to be circle, right? Circle, which comes from the equation itself, right? So you can draw the traces first, and then you can combine all of the traces to get the shape itself, okay? That's the idea how we draw them, actually. But I'd like to show you another cylinder following this definition. Is that another cylinder? Yes, guys. Why? Why we call the cylinder? It says, look at that. A surface that consists of all lines that are parallel to a given line. Let me show it to you what I mean by that. This time, I will use something like that. All right. This is what we call, guys, elliptical cylinder. So the line, as you see, this is the red line is the x-axis, and all the line, as in the definition, right, passing through, right, consists of the cylinder itself, will be parallel to the, right, will be parallel to the x-axis. That's what it means in the definition. That's why it is called the cylinder. And also, if I take the what? If I take a x equal 4, let's say, yeah. And then let me remove that one. You see, if I take the traces of this, right, shape on x equal 4 plane, right? What is the trace of it? Trace of is just a parabola, correct? It is just a parabola. You can take the trace on here, x equals 0, which is the exact YZ plane. On the YZ plane, as you see, the shape itself says so. Well, z is equal y squared, which is parabola. What you do, you just take each parabola on each plane, and then you combine all of them to get this shape, right? To get this shape. No, we call the ellipse, okay, because of another reason. Don't worry about that, all right? Don't worry about that. I'm not going to get into that discussion. What we call the elliptic cylinder, okay? That's what it's called. Yes, from the definition, right? Basically, okay, that doesn't mean the other shapes, which is not the cylinder, does have the same traces, right? When you look at the traces, in one direction, as you see, right, it's going to be all same. Your job is to look at the traces and then combine all of them. But there are some other shapes, I'm going to show it to you. You can find some different traces, and then you still need to combine all of them. But I want you to understand at least, okay, what we mean by the cylinder, guys, all right? What do you mean, Alex? Is it any shape with a one unbound axis? I didn't get that. This is unbound axis, as you see, x is equal unbound, right? There is no bound on it. Why? Since the x is missing in your term, in your equation. If it is missing, you can give any point. You can give any value to the x. As you see, I gave the x equals 0. I get to write this traces. But if you give another traces, x equal, right, the 4, for example, right, you get another traces. So if you combine all these traces, you are going to get your cylinder, right? That's the idea behind how I got. If I had, no. That's not the cylinder. Look at the cylinder definition. It says, right, in the cylinder definition, a cylinder is a surface that consists of all lines that are parallel to the given line. What is the parallel line in my case? In my case, parallel line is the x-axis. I showed you, right, the all lines which creates, all lines in my case, right, which creates my shape, they are parallel, you see, they are parallel to the x-axis, you see. If you combine all these, right, red lines, you can also get the cylinder, this cylinder. And then they are going to be parallel to the, right, the x-axis. But in your case, in your question, Alex, you said sine y. Can you find this type of parallel lines always? Or can you find an axis which all these parallel lines all these lines are parallel to the z-axis, you can't call. All right, so there are some other shapes. I'd like to introduce you in this way, guys. Just give me 1 sec. We are going to learn these shapes in this way. All right. I'm going to show you a nice table now. And then I want you to take the screenshot of this right now, although I'm going to share with you, okay, later in my notes, but we will use this now to solve a question. If you take the screenshot, that would be great. That would be great. All right, look at all these shapes. You see? You can see some of them around actually, right? As a plant, as a nuclear reactor, look at the hyperboloid of the one sheet, right? Or as a, like the satellite, elliptic paraboloid, or the hyperboloid of the two sheets. One sheet could give you, right, a satellite. So to build or to produce those type of plants, those type of shapes around, okay, they use all these maths. So the problem here, guys, when I look at all these shapes, or if somebody gives you just the equation itself, how could you draw it? How could you draw it? I just showed you, you need to get the trace right on the plane so that you can draw them. But if you would like to differentiate all these shapes, you need to understand first of all these shapes, okay, needs to include the square of the any terms, okay, square, since those are the quadratic surfaces. The main differences between them is gonna be sometimes their sign of these terms or their power. Look at the ellipsoid. In ellipsoid, all ABC, right, are positive, right? They're all positive. You see? Positive, positive, positive. X, Y, Z, they are all positive. And if you look at the cone, you see the equation in this way. But if you move these right to the other side, the coefficient of X and the Y are going to be negative, correct? But you can keep on the right-hand side. And also, equation doesn't need to be in this way. You can change. Is someone late for the class? If you want to, okay, change the variable, look at that. If this is Z, I can change that Z by X squared, whatever it is I have at the bottom, and then Y squared, and then Z squared. You see, you can put the numbers. Numbers is not important, okay? You can just ignore them. The shape form is important for us. Now look at that. Now what happened? You just turn the shape actually 90 degrees, right? Did you get the idea? If you look at here, still I have the, but the shapes sign, the coefficient sign are different this time. Now, this is the cone and an ellipsoid. Now I want you to look at it in this way. This part, these are the paraboloid. What is the common thing in paraboloid? If you look at paraboloid equation, they include, look at that, they include a term without square, right? A term without square. The other two terms, I have square, but for one term, I don't have the square. It is like one of the cylinder, but in cylinder, right, one of your variable were missing. I haven't missed any variable here, but one of them has just the first power. If you look at these hyperboloid, these are the hyperboloid. All of the terms actually has a square. They are all quadratic terms. What it differs, look at that. This is plus, this is negative. But here, okay, these are both negative. All right, these are both negative. That's how you can differentiate, okay, all these shapes actually without memorizing all these ones. As you see, they are all they're similar to each other. They all either include the X square, Y square, Z square. except the paraboloid. Paraboloid doesn't include, right, the square, one of the terms square. But they change by the, right, the sign of the variables. Now, you need to get this heuristic approach, guys, instead of memorizing everything, all right? What I want you to do now, I hope you got the screenshot of this. Now let's look at this question and then solve it together. I want you to match each equation by each shape. Let's start together. I don't know what's going on sometimes with my pen. Just give me 1 second, guys. Please.
It says that you're using an eraser, not a pen.
Say it again.
It says that you're using an eraser.
Yeah, Professor, we need to.
But the button on actually on here, it should fix my eraser. That's why I'm complaining about it. There are a couple buttons here, okay, on the side of the pen. When I press it, actually, it should fix it, but it didn't fix it. Now, okay. All right. Would you like to help me? Easiest to match is 27 to 8. 27 to 8. 8, 8, 8. Where is 8? Alex says 27 will go with 8. So this is 27. Do you think in this way? Why? As you see here, y is missing, right? Y is missing. And then that is why it should be cylinder, right? And there is only one cylinder right here, which is 27. Perfect. If you look at the right, first two, like I said, never mind the numbers, okay? Ignore the numbers for a moment. And then now look at back to that table I gave it to you. If all of them are positive, as you see, right? Positive, 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 positive. They are gonna be ellipsoid, right? They're gonna be ellipsoid. Exactly, Matthew. So I have two ellipsoid here. Like I said, since we ignored the numbers, I'm not gonna match the each one. So ellipsoid and then ellipsoid, look at that. I can just clear them out. Yeah, it could be, but I don't want to confuse your mind right now, okay, with the numbers, okay? We need to just adjust the numbers here to get the which one is bigger, which one is the smaller one. And you are right, 21 goes actually with 8, and then 22 goes by the other way, or the other way around. Doesn't matter. Now you need to learn as the first part, okay, how to match them. Okay, what do you think about the 25? 25. 25 is in the form y is equal to x squared plus v squared. Look at your table and then tell me what that would be. Huh? Jake says this is 6. It's 6. Yes. Why? As you see, this is one of the paraboloids, and then this sign is the plus. If you use your traces, look at 2x squared. Let me use, for example, z is equal k trace. Trace. Z is equal to K in 25, guys. Y is equal to 2x squared plus K squared. As you see, this is parable, right? If I use x equal K squared, and then this time it is going to be equal to 2K squared plus Z squared. So on both ways, it is going to be parable. So this is going to be the elliptic paraboloid, right? This is elliptic paraboloid, this one, 25. Did you get the idea? Do you have any problems so far? Are we doing good? All right. Let's go ahead. Thank you. Alex says 5 goes 28. And Matthew said 26 is cone. 26, let's look at the 26. Yes, all of them are square, as you see. On one side, I have the y squared, and then on the other side, I have the right x squared. As you see, guys, if you look at, right, if you give the z is equal 0, for example, right, as a 20 what? 6, yes. If I give the z is equal 0, like k, that would be equal y squared, which is equal x squared, and then either y is equal x or y is equal negative x. The trace will be just the line as in the cone. So that's going to be cone. This is what? 26. This is 26. So I can delete them. And then I did this one as well. So I have 23, 24, and then 28. Right? So if you look at the table, right, when I have one or the two of them are negatives, they were the hyperboloid, right? Hyperboloid. If two of them are negative, let's remember the table. Just check out the table. If you remember the table, where is my table? Who stole my table? Yeah. If you look at two of them, if two of them are right, the negative on the one side, that shows me, right, that that's the hyperboloid of the two sheets. So if you look at the 24, I have, right, the two negative here. That goes this one. This is 24. And the other hyperboloid, which it is this one too, right, that's going to be 23. Did you see that? All right. 28 hyperbolic paraboloid. Exactly, that one is equal 28. You see, guys? So y, since if you say y is equal, for example, k, that's going to be the hyperbole, okay, on each side. So first of all, of course, you need to make more practice, okay, for this type of problem. But at least, okay, just going over the sign and then powers, okay, you can get 80–90% idea, okay, what it looks like, right? That's going to be the first part, actually. Next time, I'm going to show you, okay, more problem about this one. So we will go to one step more. But at least, okay, we can understand the powers and then sign. It will give you some idea. These are the some shapes we know exactly, okay, what they are. Of course, in surface, okay, you can shape any, right? You can draw any shape, but we don't know their mathematical representation. But there are some guys I can show you later as well. Well, look at that. Like this one. In optimization problem, people use a lot of different things. Do you see? For example, this type of shapes. This is one of the optimization problem, actually. People try to find out what is the minimum point, okay? There is a lot of valley and then right the hill on this shape. And then we know actually what is the function for this shape. And then also this one, for example, this is another one. Rastrigan, yes, Rastrigan. This is another famous one. This is another famous one. This one, okay, Shakel. You see, there are lots of different shapes, actually. We know what they are exactly, but there are some we don't know exactly, okay, their shapes, their mathematical representation, okay? Some of them we know, but some of them we don't know exactly. And then, of course, finding the minimum and the maximum are going to be some problems. We will see later in the derivative case, but you will see that those are going to be the tools, okay? They are so restricted tools. It is not going to be always helpful. That is why, okay, we have the heuristic method like the genetic algorithm. if you have heard about, okay, before, I don't know. But you can use, right? You can use this. Let me show it to you. One of these things. Yeah, let's say this one. Negative z squared. All right. Did you see that, guys? This is hyperbolic, right? One of the hyperboloids to one sheet. Does it look like some shape around you have seen so far? Huh? Did you see? Like a nuclear reactor, right? They use this type of, right, the structure for the nuclear reactors. All right. That's all I want to say today, guys. All right. But next class, I'm going to show you, maybe I'm going to spend maybe 10 minutes more, okay, on this stuff. But later, we're going to close the chapter of the 12. It was all about, right, look at that, the vectors and then 3D shapes. Trust me, all the games you play, okay, around, they always use, okay, this type of, right, equations behind in the game engine to translate, okay, to show you the different angles, something like that, to scale up all these ones, okay. Behind that, we have all these, okay, tools, all these analytical geometry stuff, all vector stuff things, all right? So if you have some curiosity about those parts, I remember 10 years ago, maybe more actually, I looked at a little bit those stuff. They were really fun, okay? You might want to look at those stuff. All right, guys, have a nice one. See you next Tuesday. Thank you.
Thank you,
Thank you, brother.
Professor. Have a good
Thank you,
evening.
Professor.
Thank you. Have a nice one.
Thank you,
Thank you.
Professor. Have a good weekend.
You too, guys. Thank you.
Professor, wait. I have a question for you.
Yeah, sure. Go ahead, Tony. Thank you.
So, are you have any questions? I mean, I want to talk to you privately. Sorry.
All right. Yes. Jeffrey? I can't hear you.
Apologies. I just had a question